Okay, good afternoon, everyone. Welcome back. This is lecture 3 of our course. And let me give you a quick review of what we have been doing so far. This is part 1 of the course. And in part 1 of the course, I want to quickly go over a few building blocks of a typical machine learning pipeline. Now, in this pipeline, there are a couple blocks. One is the prediction model, which is something that I'm showing in the middle. And then we have a loss function. And then there is a feature extraction unit that's also an optimization method. All right. So there are a couple blocks here, and I want to go through them by showing you one very simple method called the linear regression. This is what we have been doing so far. Okay. In lecture 1, we talk about what that linear regression model means, and then we go through some geometry of that linear regression model. And then last lecture, we talk about regularization methods. How do you handle situations where your data matrix has dependent columns so then you want to have some regularity of your prediction variables. So that is about the loss function. You do something to the loss function. And then this lecture, we are at lecture number 3. We want to study a thing that's related to feature extraction. The thing that we are going to study is not exactly about feature extraction, but you can view it as one way towards that goal. Okay, we will have a few more lectures really dedicated to talk about feature extraction later on in the semester. But what I want to do today is talk about one very useful thing is now given a linear regression model, you know how to design the loss function. How can you extend it to handle nonlinear behaviors? Which is something very useful because why should all these variables be linearly combined to give you the observation? Can we have some nonlinearity? This is also a very important part of a machine learning algorithm, which you really sit down and then you dig through the feature vectors and say, hey, this feature vector is useful. And usually this feature vector comes from some nonlinear transformation of the raw data. Okay, so we want to spend some time understanding, okay, under this extremely simple setup called the linear regression, how can nonlinearity be used? Okay, in a linear setting, how can nonlinearity be used? And then the following 2 lectures, we will go into some basics about optimization algorithms, which will be like a backbone of all the methods that you are going to study in the semester. Okay. So after this part 1 of the course, I hope you get a very clear picture of what are the necessary components that you should look for in a typical machine learning pipeline. Okay? And so when we study other methods, you should have an idea that, okay, this refers to this prediction model, this refers to selecting a different loss function, this refers to selecting features, this is actually a trick referring to the optimization method. Okay? So I hope that's the goal of part 1 of the course. All right. So let's go into the material. This is the outline of this lecture. We want to look at a method called the Kernel Method. Okay. So in this Kernel Method, I have a subtitle here, which is called the enabling nonlinearity. And there are 2 parts of this lecture. The first part of the lecture is to talk about this kernel method in general. What do I mean by kernel method? How can this kernel be used in a linear regression setting? And it's actually a very simple trick to the linear regression setting if you pay attention to the formulation. Okay? And then we want to talk about a few examples. Some examples that is pretty well known if you've taken another machine learning course online before, but I want to put it into the perspective of linear regression. Okay, normally when you think about this, a kernel method is always associated with support vector machines, okay, SVMs. But I want to make it clearer that this kernel method is extremely general. It even applies to simple methods like linear regression. I want you to get that picture So that when later, when we go to talk about SVMs, it won't be a new creature to you. Okay, it's a very integrative part of the entire pipeline. All right. Okay, so what is the goal here? Why do we want to study another method? Well, the linear regression that we have been studying so far is like a global model. You give me some data, and then I try to draw one line that fits all the data. Okay, so this is, once you give me the model, there's nothing that you can do further. Okay, maybe you can tune about the loss function, but that's all. Okay, but in some of the problems, you may not want a global structure. You may want to have some kind of local structure. So I'll give you some data points. I also want to follow some kind of linear model, but I also want to encapsulate the local structure that is surrounding your neighborhood of your data points. Okay, so this is really like the basis of this kernel method, is that you want to create a kernel, a thing called a kernel, surrounding a few data points, and then build some model, and then do some prediction. And as you move to another set of data points, even inside the same data set, you will have some different predictions. Okay? Okay, so this is a localized model, and it's based on a neighborhood of data points. That would be the picture that you should have. Another thing that I want you to put in mind is that the difference between the linear regression that we have seen so far. It is more about a column space perspective, where you treat the data as many columns. Each column is a feature vector. Okay. Now a kernel method is the opposite, is the row space perspective. All right. So if you want to draw a diagram to visualize that, this is the linear regression, the ordinary linear regression, column space perspective. And then what we are going to do is the row space perspective, which is trying to look into each individual feature data vectors. Okay, each data points, and then make the prediction. Okay, so here I mean that there's a column perspective. There's also a row perspective, and hopefully by doing this kernel method, we can also gain additional capability of handling nonlinearity. That's the goal. So on the picture I'm showing here is a distinction between the linear model, okay, and the typical linear model, you have data points, you draw a line. That's the ordinary linear regression. The one I'm showing on the right, that is the kernel method, okay. So the kernel, by kernel, I mean that it's really like the orange lines here. You go to each data point, you draw some Gaussian shape or whatever, okay, and then make a prediction there. Okay, so how do you visualize that a little bit more carefully? Well, you can think in the following way. Suppose in this space you have a group of data points. Let's call them the xn's. Okay, so you have a group of data points, they are xn's, and then what do you do? Well, you try to create a surface. Okay, so for these xn's, correspondingly, they are all the yn's. Yn's are the height of the value. So x will be your input. Okay, it will be your images, and then y will be the prediction value. It could be some label or some other measurements. Okay, so it's always a pair between x and y. And then now, given all these data points in x, and then you try to draw a surface that covers all the y's. Okay. So if a new data point comes, what do? Well, you go to the x space, you locate the position of that x, and then you go up. Since you have already drawn that surface, you know what will be the predicted value. Okay. Now, of course, the key is to draw that surface. Linear regression says that I'm going to draw the surface by just looking at all the data at once. Global structure. Okay. Kernel method says that I'm going to do this locally. I will still draw the surface. It will be a different surface. And we'll do the surface drawing locally. And then once a new data point, I will just grab your neighborhoods and make a prediction. That is the picture between a linear regression and a kernel method. Okay. So, let's go into some technical details slightly. Okay. Now, there are two questions we want to ask. Okay, now you have a picture. So now let's go into the equations. There are two questions. One, you want to have a model Okay, you want the model to be what? Well, the model would be your theta. Theta would be your model parameter. You want a model, and you want this model to be somehow be derived from the data points. Okay, and that's why we have this equation here. You have the data point. You have the data point xn, and then you have a theta hat. Theta hat would be a model parameter. You want to write it in terms of a linear combination of the data points. Okay. Now, why linear combination? This is just a model. It's a linear model, right? We're still living in a linear regression world, still linear model. So we want to follow this simple approach. And now, the interesting thing is that previously, your theta hat would be like a pseudo inverse of your data points. But now, it will be strictly like a linear combination of your data points directly. It's no longer just the feature vectors. It's directly on the rows of your matrix. Okay, so this is what we want. Now, I haven't talked about how can we get there. Okay, so that would be question 1. Okay, question 1 says, how do we ever get to this expression? So we just keep that question in mind. We will address that. Question 2 is, okay, give me this theta hat. How can I make a prediction? Now, this question is a little bit easier because you give me a theta hat, and then the prediction would be theta hat transpose your data point, okay, like this. So if you have data point x, then you will just do the transpose theta hat. That would be your predicted output. Now, how do you do that? Well, just plug this equation here, then you will get that. This is just the inner product between your point, okay, yourself, and then your training data set. Okay, all the points in your training data set. Now, the interesting thing is this alpha. Of course, we haven't defined what alpha are, okay? But imagine that this alpha, what is the size of this alpha? Well, you have n data points, and therefore every data point you have one alpha, so you have n alphas. Okay, so you have a lot of alphas. And since we want to have some local behavior, you want the alpha to be localized to someone surrounding you. Okay, so you imagine that most of the alphas are 0 for you, okay, and then some of the alphas may not be 0. Okay, so there will be some localization going on in your prediction model. Okay, so let's look at these two questions. Okay, question 1 is, how can I ever write my prediction model as a linear combination of the input data points, something that is not so trivial if you think about the linear regression equations. Right? Question 2 is, fine, I want to make a prediction, then how can I determine this alpha? I need to find out this alpha. And how can I do some trick over here so that I can do the nonlinearity problem? Okay, so you can encapsulate the nonlinearity into this formulation. There's actually a very simple trick here. Okay, just replace this inner product by something what we call the kernel. Okay, so these are the two questions, and let's address them, and hopefully after addressing them, you have an idea of what this kernel method really means. So question 1 says, I want to show that this theta hat can be expressed as a linear combination of my input data points. Okay, and now how do I do that? You need some linear algebra. Okay, it's not a lot of steps, it's some steps. It's given in this technical lemma. Now, let's look at this technical lemma for the moment, and then let's see if we want to go into some details later on. Okay, so in this lemma, there is an equation. There's a left-hand side, there's a right-hand side. Okay, now, the left-hand side equation is what? The left-hand side equation is nothing but the linear regression solution, the pseudo-inverse, right? Now, the right-hand side is kind of similar. However, I put the transpose in a different place. Okay, so you see that the transpose is somehow swapped. Because you're swapping the transpose, this A transpose will go outside. Okay, not inside. It will go around this matrix. So why can this result be useful? Okay, so that you're puzzling. Why are you spending time talking about this equation? Well, we'll get there very soon. Okay, but before we get there, I want you to pay attention to the size of this identity matrices. The identity matrix on the left-hand side is what? Is D by D. If you think about your A matrix has a dimension of n by D, right? It would be the number of columns. Okay, so that would be a D by D identity. Here you will have an n by n identity. So this identity is not the same as that identity. This one it could be bigger, it could be smaller. It depends on whether your A is a fat matrix or tall matrix. But they are different. Now, you may say, why do I want to put an I here? Can I just ignore the I? Well, if you ignore the I, what will happen? If you ignore the I, there's only one way that can make it true, which is that this A has to be a square matrix. Okay, all right, because to have A transpose equals to A transpose A, you must have them being a square matrix. And in addition, you also want them to be invertible. So A inverse will equal to A transpose. So that's just not very interesting. Okay, so you do want to put a lambda here so that this equation will make some sense. Now, the proof is given in the appendix of the set of slides, okay, which you're encouraged to read. But I want to talk about why this can ever be useful in our problem. So let's take for granted that this equation can be proved, which I have proved in appendix. Then what you can do is the following. You can start with the linear regression equation, the pseudo-inverse that we saw in lecture number 1. Okay, this is the equation in lecture number 1. I call it the primal form. Now, don't be confused if you have taken a convex optimization. Okay, this is not the primal dual solution that we talk about in convex optimization. It's just another term for this particular problem. Okay, it's called a primal form for this linear regression, which is a pseudo-inverse. You have a measurement vector y, and then you take the pseudo-inverse. That would be theta hat. Okay? Something that we have derived using just taking the derivative setting to 0, or if you like the geometry picture, you use the orthogonality principle, you can derive that. Now, because of the lemma, a technical lemma, I can write this equation as that. Do you guys follow me? Okay? These two are equivalent according to the lemma I've just shown you. Okay? This is called the dual form. Okay? It is somewhat different from the primal. However, they will have the exact same result. Okay? They're the same theta. Now, let's do some calculation. Let's define the later part. Okay, usually talk about the part here, but now let's look at the later part. I'm going to define it as alpha. Okay, now it is a vector. Why it is a vector? You have a vector here, you have a matrix inverse times a vector, it will give you a vector. Okay, so I call this vector as alpha. Then what do you have? Then you have A transpose alpha. See that? Okay. So A transpose alpha. So what is A transpose alpha? Now, remember what is A. A is your data matrix. Okay. Each column represents a feature vector. And then each row represents your data point. So A transpose would be what? Well, I can write this A transpose as a matrix. There's a transpose outside, and this is your A matrix. It will be a collection of all the row vectors. Okay? So this A will be represented in this way. You have all the rows, you have n rows. Then let's look at this alpha vector. They are just a vector of all the elements from alpha 1 through alpha n. And then what? Well, then you are going to form a linear combination of those. Okay, why? Well, these are what? Well, these are you can think them as, so now you have a transpose here, right? So if these are the A matrices, and then if you take an A transpose, it will become a column. All these rows become column vectors. Okay? So you have this A matrix. Since you put a transpose outside, you will turn this A matrix into a matrix that contains each column will represent the data point. And then now you're forming the linear combination of all these data points. That will give you this, summation of alpha n and xn. This is how you can get to the expression I want. Right? Nothing magic behind. It's just a very simple technical lemma that can turn your linear regression solution into another form, which is called the dual form. Okay? And then now suddenly you can write this theta hat as the linear combination of your data points. You can do a sanity check here and then see what is the dimension of theta hat. The dimension of theta hat is the dimension of your x. It's the dimension of your input data. So nothing goes wrong. Okay? Originally, in the linear regression case, in the original primal form, you also have the theta hat being the dimension of your data point. Here is the same thing. It's just a different way of constructing the same theta hat. Now, at this point, you may ask, well, then what is alpha n? Well, alpha n is just the nth element of this vector. And you can calculate this vector, which is this inverse times y. And so I'm showing you here that this is alpha n. The nth element is the nth element of this vector, AA transpose plus lambda I inverse y. That is the alpha n's. So at this point, you have reached the goal. One, you have found a dual form. This dual form will take that linear combination of data points. Number two, you have also explicitly found the equation of this alpha n. Nothing dark, nothing magic. It's just following very simple linear algebra. It's still in the linear regression setting. Question?
For this to be linear combination, alpha n has to be independent of data points, but it is dependent on data.
The question is, should there be any independency or dependency on the data points? And it does not matter because I have a lambda here. Okay, so this matrix is always invertible given any positive lambda. See the point? Okay. Now, if I do not have the lambda, then we need to run into the question that you have, whether you can invert the matrix or not. But before that, we need to address another question. If you do not have that, then this inverse will only hold, this relationship will only hold when your A is invertible. So there's an implicit assumption that when you try to do without a lambda. Okay? All right. So that's question number one, right? So we have addressed the question number one completely. We have given you the form. We have also given you the expression of the alpha. Now, let's also go to question number two, which is more tricky. In fact, the idea is not that bad, okay? The question number two says, then can you give me some nonlinear capability to this equation so that I can handle the difficult situations? And here goes to the thing called the kernel trick. Now, we saw in the previous slide that if you want to get a predictor value, what you do, you just take the transpose of your theta hat times your new data point x. Then you can form this linear combination, which is the combination of all these inner products. Now, if you're still struggling, how do I get this inner product? You realize that this theta hat is nothing but summation of alpha n xn. And so if theta hat transpose x would just be thus xn, take a transpose with x. And this is nothing but a summation of alpha n. Xn, take a transpose with x is just the inner product of xn and x. All right, so that's how we can get to this equation. So now the idea of the kernel trick is extremely simple. The idea of the kernel trick is that look at this inner product, replace by something else. And this something else is denoted by a function called k, x, and xn. And this k is a function that takes two inputs, x and xn. It will give you some other numbers. Okay, this is called a kernel. And kernel, in a very abstract sense, it is a measure of the distance in a new space. Okay. So originally, you will have two data points in certain space. Now, you want to measure them according to some metric. So you just transform them into a new space, and you take the inner product in a new space. That would be the kernel. Okay. So think about it, at the bottom of this slide, I'm showing a point that in particular, a valid kernel takes the form of the inner product of the transform of two data points. So here is a pictorial illustration of what I mean. So think about you have two data points. They are living in R2. And then I want to measure their distance according to certain kernel. Okay, kernel meaning that I want to measure the distance using some ways. Okay, it could be that you take the Euclidean distance and then you put a Gaussian function on that Euclidean distance. Do something. Okay, so you want to measure the distance in that space using a kernel. This is equivalent to if I first transform the data point from the R2 to R3. R3 is just some arbitrary thing I make up. Okay, so you're trying to transform your data point from one space to another space. Now, in the other space, this is called the phi on your data point. Okay, so these are transformed values. In the new transformed space, if you take the inner product, the simple inner product, the standard inner product in this space, so that means you're taking the inner product of this phi or xi and phi or xj, this inner product will be exactly equal to your kernel calculated in the original space. Okay? So a kernel should satisfy this property. So now what you can think about is this. You have a data point that is living in R2. Okay? I want to do some transformation so that now the data points will live in R3. It's a lifting. Okay? Normally you think about reducing the dimensionality, but in a typical kernel method, you actually expand the dimensionality. You turn this feature vector x, you turn this raw data x1, x2 into something I call a feature vector. Okay, it's a nonlinear transformation from x1, x2 to, for example, x1 squared, x1 times x2, and x2 squared. Now, why is this set of numbers? Is another just particular example. Okay, but you can do all sorts of things by defining your own phi function. This is a nonlinear transformation. And once you have defined that, you can define your kernel because the kernel is just the inner product of your nonlinear transforms. Okay? And once you have the kernel, you go back one slide. What you do, your prediction is that simple. Okay? Just replace your inner product by the kernel. Now, of course, when you replace that, you also want to replace how you calculate the outverse, which we will talk about that. Okay? Before we go there, let me just give you a quick slice on how does, if you're still wondering, okay, what kind of kernels that we should try to imagine, I will give you two examples. One example is this a kernel that takes two vectors u and v, and then you take a transpose, take a square. So this is can it be useful? Well, we will wonder that later. Okay, but that is one example of how kernel can be defined. If this is, I tell you this is the kernel, right? Then we want to ask, what is the corresponding nonlinear transform? Can we find the phi out? Well, you can follow these steps by showing that, hey, this is the kernel. It's according to my definition. I can write the definition using the transpose, and then since you have a square, you have two of them. And then you can expand them out, and then you can write them as this two vectors. And now if you do this transformation of u to this phi of u into these numbers, then you will get a kernel. Okay, this is just one of the many possible ways or many possible examples of constructing a kernel. Can this be useful? Let's work with them later. Okay, but this is one example showing you, given a kernel, is it possible to find a phi matrix? It is possible. Now, under certain conditions, you can find that. It's not always possible, but in this case, it's possible. Another example, this is more useful in practice, is called the radial basis function. I guess some of you have heard this name before. Okay, a radial basis function, it is another kernel. Okay, remember, kernel is nothing but just a measure of the distance between two data points. As long as you give me u, and then you give me v, all right? If you give me u, you give me v, I measure the distance, I'm good. It will be like a kernel. So in this particular kernel, RBF, I take the distance between u and v. I take the 2 norm square distance, and then I put a Gaussian function on that distance. I define it to be my kernel. I can do that. And if you want to show, hey, what is the corresponding nonlinear transform? It's doable. It's shown in the appendix. It's just a little bit tedious. And you can show that the nonlinear transform is an infinite dimensional transform on the input data U or V. If you do that, you can get to this kernel, radial basis kernel. So this is a kernel. Now, the more useful thing is to have some pictorial understanding of how this kernel can fit into, one, our original problem of doing this localized prediction and things like that. And number two is how can this be plugged into our equations, right? So the shape of this kernel is like this. You have some data points, you draw a Gaussian shape around the data points, and you try to get some numbers from that, okay? What is the radius of this kernel? Well, that's defined by your sigma, okay? After 1 sigma, you have the 68% drop. After 2 sigma is 95%, 3 sigma is 99% drop. So that will somehow define the radius of your kernel. So if you make the sigma really, really big, that means you want to embrace more and more friends near your neighborhood to make your prediction. If you want the sigma to be extremely small, then you're just locally looking at a few friends. Okay? Now, choosing this Gaussian kernel is not necessary. Okay, you don't have to choose a Gaussian kernel. You can choose a Laplacian kernel. You can choose any other kernels. This Gaussian kernel would define the nonlinear shape of how you want to predict. Then we can move on and talk about how can you actually implement this kernel idea into the equation that we have seen so far. Okay, so the idea is the following. You first pick a kernel, like the radial basis kernel, okay? Or you can go online and say Kernel Method, and Google will give you a list of popular kernel methods, okay? And there you can look at which kernel you want. So you pick a kernel, and then you construct a thing called the kernel matrix. Now this kernel matrix is nothing but just applying the kernel to all the pairs of data points. Imagine that you have n data points, you just do an n squared calculation of every single pair calculation. Okay, pairwise distance. Once you constructed that matrix K, what do you do? Well, originally, what you have is that you have this alpha equals to A transpose plus lambda I inverse times Y. That is your alpha. Now, you replace that AA transpose by your kernel. Now, why can I do that? Well, imagine that, what is A? Well, A contains all the rows of your data point. If you do AA transpose, you're doing the inner product between pairwise data points, right? You take a pair of data points, you take the inner product, that would be the AA transpose. Now, if I replace that AA transpose, all the inner products by the kernel, that would be the K matrix. So this, I replace it by the K matrix. Okay, so that is the kernel. Okay? Or in other words, I am replacing this Xi and Xj, which is the ijth element of this AA transpose matrix, by a kernel on Xi and Xj. You see that? Okay? So now I get a kernel, I get the inverse. As long as I have a positive lambda, that can be invertible. I get the alphas, and then I go to the prediction, and then I replace my predictor using the kernel, get a solution, okay? And then you get a predictor value. That's the kernel method, okay? And at this point, you have accomplished all the goals that I stated in the beginning. One, you wanted to use the rows of your matrix. It's a row space perspective. Two, you want to have the local property. Three, you want to encapsulate the nonlinearity all at once using this simple trick. See that? Okay? So that is the fundamental of a kernel method. You can use this for linear regression. You can use it for support vector machine. You can even try to analyze a deep neural network using this perspective. Okay? Because deep neural network, they are more or less doing things locally on your data points and then grabbing your neighborhoods and then doing some predictions there. Okay? So this kind of kernel perspective has been proposed in the literature recently.